Hello and welcome to another digital design class. In the previous class, we spoke about the implementation of Boolean algebra using logic gates. Today we will continue that. And I'm sorry, just give me a second to fix my screen. Okay, can you see? Okay. So today we will continue with the implementations, also different functions. And I would expand different logic gates, the logic gates with multiple inputs and how they work. And I would speak about different type of logic gates, the TTO logic gates, and some of them work on high level, some of the high level voltage, and some work on low level voltages and so on. And after that, we're going to go and continue with our labs. So today I will finish chapter 2. And next week, we would start with chapter 3. So we learned that using Boolean algebra and the Boolean functions and the theories, we can simplify a Boolean function. And by simplifying a Boolean function, we can reduce the number of gates, which is going to help with reducing the power consumption, the increasing the speed, reducing the cost, and so on. Now, for the logic operations, another thing that I want to expand on is different type of logic operations using n bits. So if we have n bits, for example, we have 2 bits, x and y, then we would have 2 in the power of n rows in the truth table of the n binary variables. So this is for just drawing the truth table. And we would have 2 in the power of 2 in the power of n functions for n binary variables. So for this example, if n is equal to 2, then the number of functions would be 2 in the power of 2 in the power of 2, or 2 in the power of 4, which is 16. So we're going to have 16 different variables for the functions, for 16 different functions for the variables. And so, for example, if we have 3, you're going to have 2 in the power of 2 in the power of 3, or 2 in the power of 8 functions. Now, we can write it like this as a truth table. It's going to be 0, 0. It's going to be 0, 0, 0, 0, 0, 0, 8 zeros, and then we're going to have 8 ones, and so on. Now, this actually shows the different combination that we can write the Boolean function. Like, for example, one combination that we have is x plus y. Another one is xy. Another one is just 0. Another one is x prime plus y prime, and so on. So if we want to expand that, the Boolean expression for all of that, f0 would be 0, f1 is xy, f2 is xy prime, x3 is x, f4 is x prime y, f5 is y, and so on until f15 is 1. So this shows all the combination that we can build using these 2 variables. And we would have 16 different combinations. And the operating symbols, you already know most of them. The AND operation is with the dot. Then we have the NAND operation. We have the XNOR operation. Technically, that's like what we call an inhibition. And then we have the XOR, or exclusive OR. And we have the NAND gate, implication gate, complement, equivalence, and so on. And on the third column, you can see the name that we have. Null is obviously if equal to 0, and the opposite of null is identity, or f is equal to 1, meaning all the meaning the output would simply be 1 regardless of what the inputs are. and 0 means that the output would be 0 regardless of what the variables are. And again, we have AND, inhibition, transfer, exclusive or, NOR, equivalence, complement, implication, complement again, implication, NAND, and identity. And you can see some explanations about it, like F00 means a binary constant of 0, F1 is X and Y, and so on. Now, just this part is just a small review of logic gates and expanding on the knowledge that we have on logic gates. So the three main Boolean expression that we have, as I mentioned before, are the AND, OR, and NOT gates. For constructing gates of other logic operations, we have to consider the feasibility and economy, this possibility of extending gates inputs. Sometimes we can do that, sometimes we can't. The basic properties of the binary operations, the commutative and associative laws, the ability to the ability of the gates to implement Boolean functions. Now, we will go back and consider some of the functions that we have in the table. As you can see, 2 of them are equal to a constant, F0 and F15. 4 are repeated twice, F4, F5, F10, and so on, F4, F5, and F10 and F11. The inhibition F2 and the implication F13 are not commutative or associative. The other 8, which are F12, which is the complement, F3 is a transfer, F1 is an AND, F7 is a OR, F14 is a NAND gate, F8 is a NOR, F6 is an XOR, and XNOR for F9, which is an equivalence, are used as standard gates. The complement is also the inverter gate or the NOT gate. And the transfer is a buffer, as I mentioned before. If you have X in the input, you would have X in the output. This doesn't have any effect on the logic of the gate. The only application for a buffer is to increase the output voltage, or what we call the drive strength or the output power. So what happens is sometimes when you have multiple gates in series, for example, at each stage, you would have reduced the voltage. So what we do is we add a buffer to increase the strength of that signal. So a buffer basically, increases signals to noise ratio, improves the signal power. And sometimes it's used actually to reduce noise as well. And the XNOR gate is also called the equivalence as well. The summary of logic gates, you're already familiar. We have the AND, OR, NOT, and buffer. And we have the NAND, NOR, which NAND is basically an AND gate plus a NOT gate. Same thing for the NOR gate and so on. And we have the XOR and the XNOR gates. You're already familiar with that. But these that we studied and you see in these tables are for 2 input, single output. And by the way, all these gates are single output, but these are for 2 input gates. But what if we have multiple inputs in the system? So if we have multiple inputs, we have the extension to multiple inputs. A gate can be extended to multiple inputs. If it's a binary operation, we can use the commutative and associative law for it. And 2 gates, specifically the AND and OR gates, are commutative and associative. So for example, if we have X plus Y plus Z, we can write it as X plus Y plus Z. Or we can write X plus Y as Y plus X. And same thing for AND gate. We can do XY is equal to YX, and XY times Z is equal to XYZ. So we can easily expand an AND gate or or an OR gate. But it's a little challenging for the NAND and NOR and XOR and NOR gate, and I'll explain that. For the NAND and NOR, they are commutative, but they are not associative. They are not extendable. So what do we need for this? We need to actually use a different law, like the De Morgan's law, to be able to find the output for that. And this is an example. We have X, Y connected to one NOR gate, and Z connected to the result of X, Y when it's connected to NOR gate. And if it was a simple OR gate, if it was like this, and connected to another OR gate, it was an OR gate X, Y, and Z, we could simply write X plus Y plus Z, and we can write it like X plus Y plus Z. But for a NOR gate, we cannot do that. We can say X is NOR with Y, and it's NOR with Z. And when we use the commutative law, the final answer would be X OR with Y and with Z prime. How did we get this? As you know, X, Y naught is X naught, Y naught, using the De Morgan's law. And when you simplify it, you get to this. And if we NOR X with Y NOR with Z, we're going to have X naught or X prime and with Y plus Z, Y or with Z. Now, and let's give these some values and see what the results are for each of them. So imagine if X is 0, Y is 1, and Z is 1. I want to find the output F1 and F2. So I want you to solve this. I'll give you a few minutes to think on it, and then I will solve it. And I want you to also solve it for X equal to 1, Y equal to 0, and Z equal to 1. I'm sorry, Z equal to 0. So for the first scenario, what was the answer? F1 and F2. Let me draw the first one with black. So if X is 0 and Y is 1, the NOR of 0 and 1 would be what? 0. And by the way, this is Z. I'm sorry. This one is Z. There's a typo here. And Z would be here 1. So 0 NOR with 1 would be what? 0. What about F2? If this is 0, this is 1, and this is 1. This is for the first scenario. So 1 and 1, the NOR would be what? 0 and 0, the NOR would be what? 1. So you can see that F1 is not equal to F2. They may seem like they are the same, but they are not the same. And if I do it for second scenario, I'm going to use green again this time. X is 1, Y is 0, and Z is 0. So 1 and 0 gives us 0 again, and 0 and 0 gives us what? 1. Now this is 1, 0, 0. 0 and 0 gives us 1, and 1 gives us 0. Again, you can see that F1 is not equal to F2. Can I go to the next slide? Yes. Now, do you know how we got to this equation? So this is X plus Y prime. Yes. This result is X plus Y prime, in parentheses prime. And the final answer is X plus Y prime plus Z, all of this, and I get another notch. Here is X plus Y prime plus Z prime. Now, using the De Morgan's law, this part would be X prime Y prime plus Z, all of that again prime. And again, this would again be X prime Y prime prime plus Z prime. I'm sorry, times Z prime. Why did I do that? So this becomes times Z prime. And now this part again is going to be X plus Y, and then we're going to have Z prime. So we get this. Again, using De Morgan's law on this part, we're going to get. Is it clear? Yes? Okay. Now, what if we have multiple NOR input gates, like what we have here? We have a complement of OR gates and multiple NAND gates, which is a complement of the AND gate. If we cascade the NAND operations, we get the sum of products. If we cascade the NOR operations, we get the product of sums. Now, for example, here, X plus Y plus Z, this is the OR gate, and then connected to a NOT gate, which we have here. If I use the De Morgan's law, what am I going to have here? I'm going to have X prime, Y prime, Z prime. Okay. So I'm going to have the product of sums. So on the left, you can see one for 3-input NOR gate, and on the right, you see one for a 3-input NAND gate, A and B. And part C, you see a cascaded NAND gate, which again, a cascaded NAND gate is a sum of product. Let's solve this one. Give me an example. Let me give you an example. So imagine we have this, and A is 0, B is 0, C is 1, D is 1, and A is 1. E is 1. And I want you to find the output F. So what is the output F? Yes, so 0, 0, 0. If we AND them, it's going to be 0. So the NAND would be 1. 1 and 1, the AND would be 1. So the NAND would be 0. 1 and 0, the AND would be 0. So the NAND would be 1. F is equal to 1. And you can use that one as well. This equation here, ABC plus DE. So ABC is going to be 0, 0, 1, which is equal to 0. 0 times 0 times 1. And DE is 1 times 1, which is 1. So 0 plus 1 gives us 1. Okay. Different ways to solve this. Now for a multiple input XOR gate, it's a little different. The XOR and XNOR gates are commutative and associative. The multiple input XOR gates are usually uncommon. And I'll explain why later on. And another thing is that the XOR gate is an odd function. What does this mean? It means it will be 1 if the input variables have an odd number of 1s. This shows a 3-input XOR gate. By the way, A and B are equal. For the NOR gate and NAND gate, they were not equal. Let's go back one step. So this, you can see that if we had 2 NOR gates, X plus Y NOR with Z, the result would be X plus Y times Z prime. But in a 3-input, it was X plus Y plus Z prime. So you can see this, I'm going to mark it with 2, and this are not equal. So 1 and 2 are not equal. But for an OR gate, they would be equal because they are commutative and associative. For XOR gate, because it's commutative and associative, you can actually expand it. So an XOR gate with 2 inputs, XOR with another gate with another 1 input is going to be F is equal to X, XOR with Y, XOR with Z. And it's the same as an XOR gate with 3 input gates. So I'm going to call this F1 and F2, and F1 is equal to F2, as you can see. Because again, it's commutative and associative. Now, the truth table for this, again, if we have odd number of 1s, we're going to have a 1 in the output. Here we don't have any 1s, so it's going to be 0. Here we have 1, so we would have 1. Here again, we have just 1, 1. Odd number of 1s, it's 1. Here we have odd number of 1s, we have 2. 1, 1. So 2, therefore it will be 0. Here again, I have 1, 1, so it's 1. Here I have 2, so it's 0. Again, 2, so it's 0. And here I have 3, so the answer would be equal to 1. So if you have odd number of 1s, the output would be 1. And for x or its opposite. Did you write this down? Can I go to the next slide? Okay. Now, in logic gates, we have different logic levels. We have positive and negative logic. Sometimes we show the ones with a positive voltage and zeros with 0 volts. Sometimes it's the opposite. We show the logic of 0 with 5 volts, for example, and the logic of 1 with 0 volts. So in some books, in some references, some computers, the logic of 1 is the high voltage, let's say 5 volts, and the logic of 0 is 0 volts or the low voltage. And in some books, in some references, you would see the logic of 0 is actually 5 volts, and the logic of 1 is 0 volts. In general, they won't make any difference. It's just a little tweak in the coding sometimes and compiling the code. So case A is called the positive logic. If we have case B, it's called the negative logic. And you can see the signal assignments and logic polarity for both of them. So we have two types, again, positive and negative logics. We have two signal values and therefore two logic values. The higher voltage 5 and the lower voltage 0 or less than 3 volts, you can say. So positive logic is going to be H is equal to 1 and L is equal to 0, and negative logic H is equal to 0 and L is equal to 1. If we consider a TTL gate, I'll explain what a TTL gate is, a transistor logic gate. A positive logic AND gate and negative logic OR gate. The positive logic is used in this book as well. So in TTL, we have usually a positive logic for AND gate and a negative logic for OR gate. This graph and these tables shows the positive and negative logics. On top, you can see low, which is 0, 0, gives you zeros. Low, high gives you 0. High, low gives you 0, and high, high gives you high. This is an example of a AND gate, and the truth table you see on the left is actually the values that you measure in the inputs and the outputs. So for example, if this is a positive, by the way, logic. You have 0, 0 volts, therefore you have 0. And in the last one, you have 5 volts, and you have 5 volts in the output. And D actually shows the positive logic AND gate, and F shows the negative logic AND gate. And you can see the truth table for a negative logic AND gate. It's complete opposite of what you see as a positive logic AND gate. So 1, 1 gives you 1. 1, 0 gives you 1, 0, 1 gives you 1, and 0, 0 gives you 1. Why? Because these are technically logics of zeros, okay? And F is a negative logic OR gate, yeah, you can see. But the voltage, again, it's going to be completely opposite that what you see from a logic of OR gate. So these are going to be 0, 0 volts, and it's going to give you 0. And 0, 5 volts gives you, 0 volts and so on. So negative and positive logic are complete opposite. Now, we rarely use single gates in computer systems. We usually use an integrated chip or an IC. Some examples of an IC, we have the small scale integration system, or SSIs, which were developed in the 60s, 50s, and 60s. They have less than 10 gates. Then we have medium scale integrated circuits, or integration, or MSI, between 10 and 100 gates. We have large scale integration, which is LSI, which is 100 to few thousand gates, and very large scale integration, which is above few thousand, few 100,000, sometimes millions of. VLSIs are, I don't know if you have heard about VLSIs. In this book, we are just going up to the VLSIs. We obviously have systems which pack more gates into an IC. They are small size, low cost, low power consumption, high reliability, and high speed. In the lab, the gates that you saw, one of those ICs, for example, the one that you saw the other day, 7404, I think it was, it packed 6 NOT gates, for example. So that is considered an SSI, which is because it has less than 10 gates in it. But if in an iPhone, for example, that has several 100,000, a chip, an Arduino or a Raspberry Pi, a microcontroller, a microprocessor, they have 100,000, 200,000 million gates. That's called a VLSI. They are low power, high reliability, and they have high speed. I don't know if you're familiar with the Moore's law. The Moore's law states that every 24 months, the number of transistors doubles. By doubling the number of transistors, you technically are doubling the speed. So more transistors that you can pack in a smaller place, you can make it faster, and you can reduce the energy consumption as well. So we have different digital logic families based on their circuit technology. We have the TTL, which is the transistor logic. We have the ECL, which is the emitter coupled logic. These are high speed, high power consumption. We have the MOS, or the metal oxide semiconductor, like NMOS, high density. We have the CMOS, which is the complementary MOS, or low power system. And we have the BiCMOS, which are high speed, high density systems, which are the newer generations. Most of these memories that you see, flash memories, are made out of, they are NAND gates or NOR gates, and they are usually NMOS. But the later generations are also using BiCMOS as well. The characteristics of digital logic families, we have the fan out, which is the number of standard loads that the output of a typical gate can drive. If you put too much load on a logic gate, you're going to destroy it. Put it this way, the logic gates that you have in the lab, you could turn on one LED with them, which indicates if you have a logic of 0 or 1. If you connect 4 or 5 LEDs to that, it cannot support it with enough power, so it's going to damage the system. So fan out is actually the number of standard loads, and depends on the output power of the logic gate. Then we have the power dissipation, the propagation delay, the average transition delay time for the signal to propagate from input to output. Obviously, we want a very fast logic gate. So the faster the propagation, the speed is, you're going to have a lower propagation delay. Then we have the noise margin, the minimum of external noise voltage that can cause an undesirable change in the circuit output. And for chip design, we have to consider some things when we are designing a chip. First of all, why is it better to have more gates on a single chip? Because it's easier to build the system. We have lower power consumptions, and we would have higher clock frequencies. For a normal computer, nowadays it's 4 gigahertz. It means that the clocking is like 4 billion times a second. What are the broad drawbacks of a large circuit? They are very complex to design. The chips have design constraints, and they are very hard to test. Meaning if one gate goes wrong, you can't test that gate, and also the whole chip would not work properly. And we need tools to help develop integrated circuits like computer-aided design or CAD tools and hardware description language or HDL describe circuits. That you're going to learn these if you have semiconductor chip design, which is a graduate class. That's it for chapter 2. Next week, we're going to start with chapter 3, which are K-maps and using a different method to minimize Boolean functions. And thank you so much, and I will see you next week.
Were you saying that Moore's